Okay guys, I apologize for the last video. I realized that something was wrong with the room. It was making the camera get these kind of waves going through it. I guess something with the lights. So I moved to a different room. So I'm in a different location now. Unfortunately, I don't have enough time to go back and redo that video again. That was actually my second time to do that video, and I didn't realize it was the room itself. I changed cameras, but I didn't change rooms. I didn't realize it was the room itself that was causing the issue. Unfortunately, because we might be on lockdown tomorrow, okay, I don't have time to go back. I'm trying to make as many videos as I can before I can't use these classrooms anymore, and I'm stuck in my house. All right, so let's get started with the next part, which is Rowspace, Columnspace, and Rowspace. So Rowspace, okay, Columnspace, and Rowspace. Let's start off first with definition. Let A be a M by N matrix. Then, and I'm going to chop it here. Then, 1, the row space, or A, the row space of A, denoted with this kind of cursive R, okay, is the span. It's the space in R, N is the space, and Rn, span by the rows of A. And B, the column space of A, denoted with a cursive C, is the space in Rm, span by the columns of A. Okay. So essentially we're dealing with a subspace either in Rn or Rm, right? So row space of A is essentially the subspace when we take all linear combination of the rows of A. And Rm is the subspace when we take all linear combination of the columns of A. We'll talk about what a node space is a little bit later. Let's look at these two first. So here I have an example. It says this. Suppose I have the A is equal to 1, 3, 2, 3, 4, and 8. I want to, what is the row space and column space of A? What's the row space of A and the column space of A? That's what I want to know. What's the row space of A and the column space of A? So if we look at the first one, the row space of A, remember, again, it's going to be the span of all of the rows of A. So in this case, span of that would be, I'm going to write this going horizontally. I have 1, 3, 2, 3, 4, 8. And by the way, if you want to write these vectors vertically, you can. It doesn't matter if you write these vectors vertically or horizontally. It doesn't matter at all. So if you want to write it vertically, you can in this instance. Now, what is this going to be? What's the row space of A going to be? Well, if we look at these two vectors, right, the linear combination of these two vectors, I think these two vectors are linearly independent of each other, right? So the row space of A is probably going to be a plane in R3, right? So it'll be a plane in R3. How do I know it's in R3? Because I have three components, right? These two vectors are linearly independent because I cannot write this vector as a linear combination of this one and vice versa, okay? So it's a plane in R3. That's my subspace that I'm dealing with here. And what is the column space of A? Going to be 2. Well, that's going to be the span of the columns of A. 1, 3, 3, 4, and 2, 8. 1, 3, 3, 4, and 2, 8, right? So I'm looking at all possible linear combination of these three vectors, 1, 3, 3, 4, and 2, 8 in R2, right? In R2. Now what is this going to be? So the row, here I have it, the row space of A is going to be a plane in R3. What's the column space of A going to be? It's going to be A, well, if we look at this, right, we have at least two linearly independent vectors, right? 1, 3, and 3, 4 are definitely linearly independent vectors, okay? So I mean, I have at least two linearly independent vectors, and I actually have more vectors than I really need, right? Because this R2 is a two-dimensional space. So I have three vectors, but I just need really two linearly independent vectors. So here I have at least two linearly independent vectors. So the column space of A is actually going to be all of R2 in this case. So the column space of A is going to be equal to R2. Which is also a plane, by the way. R2 is a plane. So the row space of A is a plane in R3, right? The column space of A is all of R2, right? Because we only have two components here, right? So the only plane in R2 is R2 itself. So that's the row space of A and the column space of A. And this is kind of the geometry of this, right? The geometry of the row space of A is a plane in R3. The geometry of the column space of A is all of R2. Notice that in this case, I want you guys to notice that what is the size of my matrix A here? What's the size of this matrix? The size of this matrix is a size, how many rows? 2, right? How many columns? 3. So this is size 2 by 3. Size 2 by 3. Right? In this case, that means that my M is equal to 2. My M is equal to 2, right? So we're going to be in R2. My N is equal to 3. My N is equal to 3, right? M by N matrix that we have here. M by N matrix. My M is equal to 2. My N is equal to 3, right? So my row space of A is going to be in R3 because N is equal to 3. My column space of A is going to be in R2 because M is equal to 2 in this case. I hope that kind of makes sense, and I'm not blowing by too fast. But I want you guys to notice something. Well, before I talk about what I want you guys to notice, let's do one more example, and then I'll talk about something in general. I want to look at an example. Is the vector (2, 1, 0) in the row space of A? Okay. I want to know, is the vector 2, 1, 0 in the row space of A? Is the vector 2, 1, 0 in the row space of A? Well, how can I figure out if the vector 2, 1, 0 is in the row space of A? Well, if it is in the row space of A, right? If it is, then there should be a linear combination of the rows of A that will get me 2, 1, 0. This is what we're saying. If it is in a row space of A, there should be a linear combination of those vectors in A, of those rows in A, that will get me 2, 1, 0. So let's look at it, see if we can. So let's see, we have to have a linear combination. So C1 times my first row, 1, 3, 2, plus C2 times my second row, 3, 4, 8. That should get me 2, 1, 0. Well, we can create an augmented matrix, right? So we have 1, 3, 2, 3, 4, 8, 2, 1, 0. We'll solve this system. What's a reduced row echelon form of this, right? Pause the video, see if you can get it, and tell me what the solution would be. Well, welcome back. What did you get when you did a reduced row echelon form? You get 1, 0, 0, 0, 1, 0, 0, 0, 1. And the solution, if you actually my system, when I wrote this out, system, is that C1 is equal to 0, C2 is equal to 0, and 0 is equal to 1. By the way, 0 equal to 1 is a false statement, right? This is false. So that means there is no solution, right? No solution. We've done these types of problems before. If there's no solution to this equation, that means that 2, 1, 0 is not in the row space, okay? Let's look at another example. Is the vector 0, 5 in the column space? Right. Is the vector 0, 5 in the column space? Right. And what we can do is the same thing we did before. I want to know, is there a linear combination of these 3 rows that will get me the value 0, 5? C1, 1, 3, plus C2, 3, 4, plus C3, 2, 8. Does that equal 0, 5? Now I know some of you guys are yelling at me. Some of you guys who finally got it. Some of you guys are yelling at me, saying, Dr. Wesley, we don't need to do this equation. We don't need to write down this equation at all to know that 0, 5 is in the column space, man. We don't need to write it down. You're doing this for no reason. Now, why don't we need to write this down? Why don't we need to write this down? Because what is the column space of A? The column space of A is equal to R squared. Okay. R squared. Is the point 0, 5 in R squared? The answer is yes, it is. Or is the vector 0, 5, can I represent it in R squared? I can, right? I can. 0, 5 is a part of R squared. So yes, 0, 5 has to be in the column space of A. However, suppose you don't know that. You're like, I have no idea, Dr. Wesley. I have no idea. And you want to be able to, you want to just do it the same way we just got through doing it. So that we can create an augmented matrix, right, for this equation. One, 3, 3, 4, 2, 8, 0, 5. So I got here, Now, what is the reduced row echelon form of this? The reduced row echelon form of this, if I did it correctly, is this. I have 1, 0, 16 over 5, 3 is going across, 0, 1, negative 2 over 5, and negative 1. That's a reduced row echelon form of that. So I have 1 and 0, 16 over 5, 3, 0, 1, negative 2 over 5, negative 1. What's my system here? Well, I get C1 plus 16 over 5, C3 equal to 3. I get C2 minus 2 over 5, C3 is equal to negative 1. Now, does this system have a solution? Well, absolutely it has a solution. I'm not going to write it down just for the sake of time, but this system has a solution. Right? This is going to be a parametric, right? I can think of C3 as being equal to T, right? So I have infinite solutions, actually. So it has a solution. That means there are values of C1, C2, and C3 that I can multiply these vectors by to give me 0, 5. Has a solution. So that means that since it has a solution, that means that 0, 5 is in the column space of A. Okay. 0, 5 is in the column space of A. Okay. Very cool. Very cool stuff. Now, what I wanted to mention is I want to go back to what we were talking about here, in this part right here. Now, notice for the first one, when I did the row space of A, right, I was able to tell pretty quickly that I had two linearly independent vectors, right? So I want to get a plane in R3. So I know that this is going to be a plane in R3. So these two vectors are actually going to be a basis, right, for the plane in R3, right? These two vectors here represent a basis for the row space of A. These two vectors that I have here, these guys are both linearly independent. No problems there. And so I know that I can generate the plane in R3 using these two vectors for the row space of A. However, the column space of A is the column space of A basis, right? I mean, are these three vectors here, I should say it this way, are these three vectors here a basis for the column space of A? And the answer you should say is no, it's not, right? Because how many vectors do I really need to be able to span R2? I only need two vectors, right? Only need two vectors. How many vectors do I have? I have three, right? So one of these vectors is redundant. One of these vectors is not needed, right? I don't need to have all of these vectors to be able to have a basis for R3, right? I just need two of these guys. And so what we want to do is, well, if I just have an arbitrary matrix A, right, how can I guarantee that I have a basis for my row space and my column space of A? Just have the vectors that I need to create a basis for my row space and my column space, right? To be able to generate either a plane or a line or a three space or whatever the column space or row space represent. Okay, and that's what we want to talk about next. How to create a basis for the row space and column space. How do we create a basis for row space and column space? Okay. This is what we want to talk about next. And so we're going to use this theorem. It says this: if matrix B is equal to the reduced row echelon form of A, okay? So I'm taking the reduced row echelon form of A, I call it B, no big deal there. Then the non-zero rows of B form a basis for the row space of A. So what we're going to do is something that seems a little bit weird. We're going to take the reduced row echelon form of A. When we do that, it actually is going to simplify, in some ways simplify our row space. It's going to get rid of any redundant vectors that we don't need. It's going to give me a basis in which we can use to be able to, for the row space of A, to be a basis for the row space of A and a column space of A. So what we're going to do, we're going to take the reduced row echelon form of A. It's going to eliminate all of the unnecessary vectors that we don't need, right? And we can use whatever is left over, the non-zero vector rows of that reduced row echelon form, as a basis for the row space of A. Let's look at an example. And this example is actually in the book, but it's a good example, so I wanted to do it. And we'll do another one kind of tying everything together at the end. So we're going to find a basis for the row space of A, where A is equal to 1, 3, 1, 3, 0, 1, 1, 0, negative 3, 0, 6, negative 1, 3, 4, negative 2, 1, 2, 0, negative 4, 2. Okay, this is okay. So I want to find a basis for the row space of A, and I'm given this as A. Now let me just kind of reiterate what we said the row space of A is equal to. The row space of A is really, when it comes down to it, is equal to the span of all the rows of A. So I'm going to write out the span. So all possible linear combinations of these 5 rows. These 5 rows. Okay, we have, so here's 3, 4, negative 2, and 1, and then my last one is 2, 0, negative 4, and 2. Now, I don't know about you guys, but I have no idea what geometric shape this is. I do know what space we're in, right? What subspace is, what space is this subspace, this row space in? It should be in R4, right? Because we have 4 components here. So our row space is in R4, so our subspace is in R4, but I have no idea if it's a line or plane or 3 space or if it's even all of 4 space. I have no idea just looking at this guy. Right? It could be anything. So I want to be able to figure out what in the world, what is this geometric object, right? So I'm going to take the reduced row echelon form of A to figure out how many basis vectors I really have. So let's do that. So the reduced row echelon form of A. Put it over here. When we do that, we get 1, 0, negative 2, 0, 0, 1, 1, 0, 0, 0, 0, 1, and then we have 2 rows of all zeros. So I have 2 0 rows at the bottom, and all the other stuff is non-zero rows. So I have 3 non-zero rows, 2 0 rows. So now I say, okay, so the row space of A, I can't write the row space of A as the span of all these vectors, but really what I can say is that the row space of A is equal to the span of my non-zero vectors I have in this reduced row echelon form. So that, like I said, it's a span of 1, 0, -2, 0, 0, 1, 1, 0, and 0, 0, 0, 1. It's 1, 0, -2, 0, 0, 1, 1, 0, 0, 0, 0, 1. Now this is going to be a basis. These are three linearly independent vectors. Now what object is this, right? What is this geometric object? And if you say it is a three space, it is a three space in R4. A three space in R4 is what we're dealing with here. This is a three space in R4. So some three-dimensional cubic or rectangular space in R4, okay, generated by these three vectors. Now, before we go on any further, I want you guys to notice that these rows that I just created are not the same necessarily as the ones I had before. There's 1, 0, 1, 1, 0 that is, right? It's the same exact one. But these two guys here are totally different, right? And essentially when I do the reduced row echelon form, what I do is I get rid of all unnecessary values that I don't need. I get rid of all unnecessary values in my components that I don't need. And I'm only left with the non-zero components that I need in each one of my coordinates to be able to span the space. However, I want to also mention the fact that if I take a linear combination of these three vectors here, that I can create any of these five vectors that I originally had in my row space. Okay, so I can use these three vectors here to generate any of these five rows or five vectors that I had before. Okay, so essentially I just keep what I need, get rid of the stuff I don't need. Let's talk about the column space of A. I want to be able to find a basis for the column space of A. So in the previous example, find a basis for column space of A. Find a basis for the column space of A. Okay, so let's do that now, right? Let's find a basis for the column space of A. And the nice thing about this is, I'm like, okay, there is a relationship between the row space and the column space. And I can say that the column space of A, right here, I'm gonna say note, it's in the PowerPoints as well. Column space of A is equal to the row space of A transpose. So that transpose is actually useful for something. The column space of A is equal to the row space of A transpose, because what does the transpose do? It interchanges rows and columns, right? It interchanges rows and columns. So my columns become rows, which is exactly what I want, and I'm going to do the reduced row echelon form just like I did before. So let's do that. A transpose, let's write it down. A transpose looks like this. I have 1, 0, what's that, -3, 3, 2. I have 3, 1, 0, 4, 0. I have 1, 1, 6, -2, -4. I have 3, 0, -1, 1, and 2. Okay? So that's A transpose. Right? I'm going to take the reduced row echelon form of A transpose. And this is what I get when I do that. Reduce row echelon form of A transpose. I get 1, 0, 0, 0. I think I have 1/2. You guys double check and make sure I did it correctly. Here I have 0, 1, 0, 4, -3/2. Here I have 0, 0, 1, -1, -1/2. And then I have a row 0, 0. Okay. So again, I want to just mention the fact that let's write out the column space of A the way you would have done it the first time, right? If I say, what's the column space of A? Okay. That's going to be equal to the span, right, of my original set, right? So the column space of A is going to be span of the columns of A, which are going to be 1, 0, -3, 3, 2. 3, 1, 0, 4, 0. 1, 1, 6, -2, -4. And the last one is 3, 0, -1, 1, and 2. Okay. Now, what in the world is this geometrically? Well, I know what space I'm in. I'm in R5, right? So my subspace, my column space of A is in R5, right? Because I have 5 components for my vector. But what type of geometric object is it, right? Just looking at this, I wouldn't really know unless I could figure out which vectors are linearly independent, right? How many I have. However, when I take the reduced row echelon form, right, it's going to eliminate all the stuff I don't need, and so I'm going to be left with this. When I take the reduced row echelon form, I'm going to be left with my basis vectors, right? So my column space of A is really going to be the span of just these 3 vectors that I have here, which is 1, 0, 0, 0, 1/2. 0, 1, 0, 4, -3/2. And the last one is 0, 0, 1, -1, -1/2. Okay. So I have 1, 0, 0, 0, 1/2, 0, 1, 0, 4, -3/2, 0, 0, 1, -1, -1/2. Okay. Those are my guys. And now, looking at that, looking at this, I can say, okay, all right, I kind of got that. This is my basis. This is my basis. These 3 vectors, 1, 2, 3, are my basis for the column space of A. So I know that this is going to be a 3 space in R5. A 3 space in R5. If you wanted to, and you don't have to do this, right? You can multiply each one of these vectors by 2. So to get rid of the fractions. Sometimes you don't like fractions. I can write this as 2, 0, 0, 0, 1, right? I can write this one as 0, 2, 0, 8, -3. I can write the last one as 0, 0, 2, -2, -1. If I wanted to. This is perfectly fine. Okay, this is nothing wrong with this. This is my basis. This is a basis for the column space of A. I got rid of any redundant vectors I don't need. These are the only 3 I really need. These are the guys I need. Nothing else. I know that this is going to be a 3 space in R5. And then I realized, hey, have you realized that here I have my dimension of the row space of A is 3. And I got the dimension of my column space of A is also 3 in this particular example. If you guys looked at that last one that we did, the first example we did with row space and column space of A, right? We got the dimension of the row space of A and the column space of A to both be 2, right? We only had 2 basis vectors for the first example I did. You guys remember that? And then you say, okay, Self, right? Is the dimension of row space and column space always going to be the same? And the answer is, yes it is. So I can always say this, the dimension of the row space of A and the column space of A are always the same. And it's denoted the rank of A. So I can say here that the rank of A is equal to the dimension of my row space of A or the dimension of the column space of A. In this case, my rank of my matrix would be 3, right? The rank of my matrix would be 3 in this particular example. Okay. Before we go to null space of A, let's look at an application of the row space. Why is it useful? Let's look at an application of the row space. Why is it a useful thing? So let's look at that next. All right, are you guys with me? Whew, you're probably looking at this in chunks, and I'm doing this like one after the other, bam, bam, bam. But bear with me. Hopefully, I'm not making any dumb mistakes, and we're gonna go for, continue on. So I can use the row space of A to actually find the basis for a subspace in R. I'm going to use the row space to find the basis for a subspace in R. So to find a basis for a subspace spanned by the vectors S equal to B1, B2 to BR, we employ the method used to find the row space of A, or the row space. Okay? We employ the method used to find the row space. Let's look at an example to make it clear. Then once we do that, we're going to go to null space. Here's my example. Find a basis B for the subspace spanned by here I have S equal to 7, -1, 0, -7, 0, 1, 0, 5, negative 5. So I want to be able to find the basis, a basis, for the subspace spanned by these three vectors, right? I'm going to look at, essentially, am I looking at a line, a plane, or a 3 space, right? What is going to be the subspace of the linear combination of these three vectors? Now, by the way, what larger space are we in? What's the largest space we're in? We're in R3, right? We have 3 components here. Okay, so this is going to be a subspace in R3. So it's going to be either a line, plane, or all of R3 that we're dealing with here. So how do we find a basis for this? Well, we have these 2 steps to be able to find a basis. Step 1. I want to create a matrix A using the vectors as rows in A. So we're going to create a matrix A using the vectors as rows in A. So if I do that, I'm going to create a vector. I'm going to create a vector. Create a matrix. I apologize. Create a matrix based off the vectors that I have here. And they're going to be put in as rows. So I have A is equal to 7, negative 1, 0. Negative 7, 0, 1. That's going to be my second row. And then my last row is 0, 5, and negative 5. Okay. The second step is that I'm going to take the reduced row echelon form of A. So I want to find the reduced row echelon form of A. And the non-zero rows will be a basis for B. So the non-zero rows of the reduced row echelon form of A will be a basis. Okay. So let's do that. So if I take the reduced row echelon form, I end up with 1, 0, negative 1, 7. 0, 1, negative 1, 0, 0, 0. Okay. Now, this is really nice because now, guess what? Those non-zero rows are going to be a basis for the subspace spanned by these 3 vectors. Okay. It's going to be a basis for the subspace spanned by these 3 vectors. So I can say, okay, these 2 guys here. So I can say a basis for the subspace is dot, dot, dot. Here I have 1, 0, negative 1, 7. And the other one is 0, 1, negative 1. Again, if I wanted to, if you don't like fractions, you can multiply this vector by 7, so you get 7, 0, negative 1. It's up to you. This is perfectly fine again. Guess what? So what would be the geometric shape of this particular subspace, right? the subspace is going to be a what? It's going to be a plane. I'll call this guy B. It's a plane in R3. Right? So again, let me just kind of reiterate this. If I take all possible linear combinations of these three vectors, it's only going to be I'm only going to be able to get a plane. I can only represent a plane in R3. And that plane can also be represented by just these two vectors that I have here. What's the dimension of this subspace? The dimension of this subspace, I should have given it a name. It's going to be 2 in this case because I only need 2 basis vectors. Okay. I should have given it a name. I should have called it B or something. Oh well, it's too late for that now. I'm not going back to doing that again. It's craziness. All right. So Buford and Genevieve are still with me. I hope you guys are too. All right. And now let's talk about null space, which is our last topic here. Null space. Okay. Let me erase this. All right, so last big topic, null space. Okay, null space of the matrix. And this is a big enough topic actually that I should just do a separate video. So I'm going to stop it right here, and we're going to pick up with null space next. All right?